The stroller's mass is given, the mass of the child and the stroller, so that's useful for calculating the force of gravity. We'll let the stroller be represented as a particle or a single point in space for our free body diagram, and we have our force of gravity. The force due to gravity must be opposed by an equal and opposite force. Otherwise, the stroller would be moving down. So what's opposing that is the normal force. But this might be a bit misleading because we have another force in our free body diagram. We have this applied force represented by the white arrow. So without pushing on the stroller at all, these two forces would be equal and opposite. However, we have an applied force represented by this white arrow. This applied force is pushing down this way, so we'll show that on the other side of the particle. Parallel and same magnitude, the applied force on the particle is this direction. And so we have to think, is the normal force just equal to the force of gravity anymore? No, it's actually a reactionary force that's being added to by the applied force. So the normal force is actually a little bit greater due to the y component of the applied force, because we have this applied force in x components and y components, and when we add the y component of the applied force, which is down, to the y component of the force due to gravity, it should equal the normal force. So let's actually just stack them up to show this off to the side here. So we have our applied force. So when we stack these up, it's kind of messy, they should equal the normal force. Or in other words, they should be the same magnitude. They should cancel each other out. So I actually haven't drawn my normal force long enough. It should be longer. Let's make it a bit longer. So that's actually the case. So we use this in the next question.